Hello viewers, you are welcome. In this video, we are going to consider what is called differentiation of inverse functions. It's very simple, trust me, but I will try as much as possible to make it simpler. So let's go on board. We are going to consider 5 different examples, but in all of them, what we are actually trying to do is like if our y is a function and that function is dependent on x. Now, the point is this: we are no longer looking for y, the y dx. We are looking for the x, the y. So what is going to be? You get the point now. You know, our y is a function of x. So what you are looking for is the rate of change in x with respect to y. You know, I can also say that, in other words, if my f of x and f prime of x, they are inverses of one another. What I mean by that, f is the inverse of f prime and f prime is an inverse of f. Then we can actually say that, so what we're going to do now is this. This will help us to find d dy of ln y, which we don't know. Even d dy of tan inverse of y. In fact, d dx of sine inverse of x. d dx of cos inverse of x, even d dx of x1 over 3. We are going to find all the 5 now. So let's proceed. Let's go ahead now. Example 1. Example 1 here, let's consider what is called exponential of x. And remember that ln y is the inverse of exponential of x. Or perhaps I can say that exponential of x is the inverse of ln y, or ln y is the exponential of f of x. So let's take a look at it graphically, how it looks like. So as you can see now, that is the graphical illustration of exponential of x. So what we are now trying to say is that there is another function called ln of y, and that ln of y is the inverse of exponential of x. But the point here is this: we are asked to learn, or perhaps let me say it this way, we want to differentiate ln y with respect to y. We want to differentiate ln x with respect to x. And what both of them will give us, they are almost similar. You get the point now? So they are similar. So we want to differentiate ln y and want to differentiate ln x. So let's follow the procedure now. So let's make x the subject of formula. So if our y equals to exponential x, let us make x the subject of formula. So next thing is that we are going to differentiate both sides with respect to x. So by the time we differentiate, the only problem now is this: we are trying to differentiate d dx of ln y. So let's keep that one. The next step will now be, we are going to break that derivative into 2. You know, we are trying to find d dx of ln y. So we can break it into 2 to give us d dy of ln y multiplied by dy dx. Do you get that? That's just the only technique here now. d dx of ln y is what we are looking for. So we're going to break it down to d dy of ln y multiplied by dy dx. You know that dy can cancel dy, so we still get the same expression back. So it's very, very correct. So when you differentiate x with respect to x, what we get is what? You get 1. So that's all. So now with that, we need to find our dy dx, because if our y is exponential of x, what is the y dx? The y dx is still the same thing as exponential of x. So we'll substitute that to replace the y dx. So, and the same thing now is that d dy ln y is what we are looking for. So we make it the subject. So exponential x will go on that one. So we substitute y equals to x back to the expression. So we now get d dy ln of y is equal to 1 over y. So this time around, let's replace y with x, which means that d dx ln x is equal to what? 1 over x. Thank you. So let's proceed to the second example. Example 2. So this time around now, let's take our time to differentiate tan inverse of y. But the point is this: what is d dy tan inverse of y? What would it give us? Let's go to look at the second one. d dx of tan inverse of x. What is it going to give us? So let's consider both of them. You can see that they are the same thing. It's just that the derivative, what we are differentiating them with, a little bit different. So for instance, the first one we are differentiating with respect to y. The second one we are differentiating with respect to x. But both of them, we are going to use the same approach, which is the inverse function, to handle them. But before we proceed, do you remember the graphical illustration of tan inverse? Okay, the graphical illustration of tan x. So let's look at the graph of tan x. But remember, during the physical classroom, I mentioned the fact that tan x, it has so many vertical asymptotes. Okay, remember that? Okay, so if you look at this graph very well, you will notice that there are many vertical asymptotes there. Remember I mentioned it. There are many vertical asymptotes there. So another thing we need to notice here is the fact that the function tan x, it is undefined at certain points on the x-axis, which means that the function is not continuous at all the points. Let me say it better. Tan x is not continuous at all the points in the value of x. So because of that, let's be specific about the domain. So the domain we are using here is minus pi over 2, pi over 2. And the reason is because we want to pick a domain whereby the function is continuous. That is why we can find the derivative. So we can just say that tan inverse of y is the inverse of tan x. So if y is equals to f of x is equals to tan x, that's where we're going to start from. We're going to start with the fact that y is equals to tan x. So if you make x the subject of formula, what are you going to get? We're going to get tan inverse of y is equals to x. So we proceed, we differentiate both sides. Remember that what we're having now is tan inverse of y is equals to x. So we differentiate both sides with respect to x. Please take note of that instruction. We are going to differentiate both sides with respect to x. But the issue now is this. If we are differentiating both sides of tan, if we are differentiating tan inverse of y with respect to x, we need to use chain rule. That is the point. So how do we go about it? We now say d dy of tan inverse of y multiplied by dy dx. Remember that dy can cancel dy, then we still call back to what we have here, which is d dx tan inverse of y. As usual, if you differentiate x with respect to x, you have what? You have 1. So if y is equals to tan x, what is the derivative? What is dy dx? If y is tan x, then dy dx is what? Is sec square x. So for this now, we can now replace, instead of writing dy dx now, we now replace dy dx with sec square of x. Of course, we can divide both sides by sec square of x. Yes, that's possible. So that what we are looking for, which is d dy of tan inverse of y, can be on our left hand side. But remember this identity which says that sec square of x is equals to 1 plus tan square of x. Do you remember that in trigonometry? Yes, I think there was something like that in first semester. So we are going to use this condition, which is sec square of x equals to 1 plus tan square of x. With this, if our y is equals to tan x, then sec square of x is equals to what? 1 plus y squared. So in this case now, we can now replace, instead of writing sec square of x, so what we are going to write now is now 1 plus y squared. Yes, so we write 1 plus y squared. So this takes us to our final destination.